All right, let's talk about resonance. So, resonance is the idea that in molecules with multiple bonds, there are often multiple valid ways to draw them. So we looked at the SCN sulfur, carbon, nitrogen molecule, and there were 3 different ways to draw that where you were always fulfilling the octet rule. So ozone, for instance, you could draw, if we labeled these oxygens 1, 2, and 3, I could have the double bond between oxygens 1 and 2 or oxygens 2 and 3. So which one is it? Well, the answer is yes. So I can transition between different resonance forms by moving a lone pair into a double bond and moving a double bond into a lone pair. Okay, so I take this lone pair, it turns into a double bond, and take that double bond, turn into a lone pair. You get to here, so still not violating the octet rule, and I can go back, right? So this is why it's called resonance, because it can flip in between these forms. And so then what's really interesting about resonance is that the actual bonds are being shared. The actual bonds are halfway in between the shared bonds. Okay, so the electrons are flowing. It's not. So we say, if we call this form A, and we call this form B, it is not A. It is not B. It is some hybrid in between of both A and B at the same time. Okay, and so the way we draw this is we draw a dotted line to show that electron density is being shared across multiple bonds. Okay, so it's a partial double bond characteristic between both these bonds. So both of these bonds are actually exactly the same, and so we would call these, like a 1.5 bond. So it's a double bond being shared between 2 bonds, and we call that like a 1.5 bond. Now there's a way to calculate this. We'll go over how to calculate this later, but yeah, if you have like a dotted line like this, then rather than it being this or this, A or B, it's both. So let's do a practice problem. So draw all the resonance form of carbonate. So we talked about carbonate, right? It's carbon, single bond oxygen, double bond oxygen. Okay, and so we can conceive of a possible resonance structure where this lone pair moves in and this double bond moves out. And this happens simultaneously, so you never have carbon with more than an octet. Okay, and that can give you carbon with a double bond over here. And then you could conceivably have this guy move in and this guy move out and get carbon double bond over here. And then, of course, this one could conceivably move in, move out, and go back to that one, right? So there are 3 potential resonance forms of carbon dioxide. So the way we would draw this, if we were being clever about it, is we'd say that there's a partial double bond characteristic shared amongst the 3 oxygen bonds. Okay, what about N3 minus, azide? So N3 minus. So first of all, we needed to figure out, okay, well, what the heck does that look like? So N. Okay. Okay. Well, if I do this, then this nitrogen is missing an octet. So if I move that there and then put that extra electron there, whoops, then I get something like right. And we can check the formal charges on this. So nitrogen, double bond, nitrogen, double bond, nitrogen. So 5 minus 6 is minus 1. 5 minus 4 is plus 1. 5 minus 6 is minus 1. So the overall charge on this molecule is going to be minus 1. So again, it doesn't matter which side we start from, but we can conceive of a double bond moving in, or a lone pair moving in, and a bond moving out. Okay, so that would give us nitrogen, single bond, or triple bond nitrogen, single bond nitrogen. Okay, this is still +1. Now this one is 0, and this one is -2. We could also do it the other way, right? So this one can go, this one can go boom, boom. So we could also think of this the other way, right? This could go in and that could go out to get triple bond on this side and single bond on this side. Okay? But as you can see with the formal charges, this one has a -2 charge. This one has 2 -1 charges. So it's a bit of a toss-up, but generally speaking, the higher ones are less favorable than having multiple smaller ones. But you can transition between these three forms, right? And so you're going to have partial bond characteristic, partial triple bond, double bond characteristic between all these bonds. Okay, let's move on to some exceptions to the octet rule. So some exceptions to the octet rule, because not everything follows this, but generally speaking, you will. But not everything does. So the first exception is hydrogen. Hydrogen only needs 2 electrons, so it follows the duet rule. It'll form one bond, and it is never, ever the central atom. Beryllium and boron don't need a full octet. They will always have deficits. So beryllium will form 2 bonds, so it'll have 4 electrons. Boron will form 3 bonds, so it'll have 6 electrons. And that looks, this is what those compounds look like. So beryllium only needs 2 bonds, boron only needs 3 bonds. Now, because it does technically have a deficit, this gives these compounds certain properties, which boron trifluoride, for instance, is a Lewis acid. That's not super important. And then, but those are generally the only deficits you're going to have. Now, any atom that has an N number higher than 3, so period 3 or higher, so starting with sodium, can have an expanded octet. If an octet is possible, it is preferable, but it can have an expanded octet. What is an expanded octet? It means 10 to 12 electrons, generally speaking. I think you can do more than that, but generally for us, it's going to be 10 to 12 electrons. So that means, generally speaking, 5 to 6 bonds / lone pairs. So, for example, phosphorus pentachloride, sulfur hexafluoride. These are possible compounds because they have an expanded octet. Any atom from period 2, like carbon, nitrogen, oxygen, fluoride, cannot, emphasize this, have more than an octet. So if you see carbon that has, like this, that is wrong, 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 wrong. Please don't do that. So let's look at some practice examples. Draw the Lewis structures for PO43- and SO3-. So phosphate and sulfur trioxide. So phosphate so again, I'm using my method. I'll also do the other method just for your sanity's sake. So we would go phosphorus, oxygen, 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 oxygen. We say, okay, phosphorus is 5 plus 4 6s. 6 times 4 is 24 plus 5 is 29 plus 3, because it's -3, is a total of 32 electrons I have. So we go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Okay, so you could do it that way, and you get -1, -1, -1, -1, +1. So that's fine, but you have a lot of formal charges. The other way to do that is if you put one of those in like this, then you get like that, and you have 0, 0, -1, -1, -1. So you've mitigated 2 of the formal charges, so that's going to be more preferable. So here I would say, okay, well, this is going to go boom, 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 and then I have 3 extra electrons, 1, 2, 3, and that would also get me there. So for sulfur trioxide, let me just start over. Sulfur trioxide, I've got sulfur 1 oxygen, 2 oxygen, 3 oxygen. Wow, I'm struggling. Okay, ignore this one. Okay, so 2, 4. Wow, let's do this oxygen. 1, 2, 3, 4, 5, 6. Oy vey. All right, so okay, so then I've got 3 unpaired electrons on my oxygens and 3 electrons on sulfur. So why don't I just hook them all up? Okay, that looked really wonky, but basically I'm saying, oh, what if you form a double bond with each oxygen? Okay, then formal charge is 6 minus 6, 0, 6 minus 6, 0, 0, 0. Cool beans. So let's do the other method, sulfur, oxygen, 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 24 valence electrons, 6 times 4. So we go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, sulfur doesn't have an octet, move that guy in. So you get sulfur, okay, 0, minus 1, minus 1, plus 2. Blech, we don't like having 2s. So let's move that one in. Okay, now we have sulfur, oxygen, oxygen, minus 1, plus 1, 0, 0. That's okay, but we can do better, right? Move that in. And again, there's resonance. So it'll be between all of those. But again, minimizing formal charges is what you want to do. So the expanded octets can get a little bit funky. They can get a little bit funky, but it's something you'll just have to practice and play around with.